Hello, and welcome to this presentation, The Role of Amplifiers in High-Power RF Component Characterization. In this presentation, we'll discuss why amplifiers play an important role in the design, characterization, and testing of high-power radio frequency components, as well as discuss the most common types of high-power RF component testing. Let's start by defining what we mean by an RF or radio frequency component. Radio frequency is generally defined as signals with a frequency from the tens of kilohertz well into the upper gigahertz range. So, an RF component can be defined as a component that transports, modifies, or terminates signals at these frequencies. Often, RF components are categorized as either active or passive components. Passive components are components that do not require an external power source for their operation. For example, filters, combiners, couplers, etc. On the other hand, active components do require external power. Amplifiers are one of the most common active components. In both cases, radio frequency components usually exhibit frequency-specific behavior. This is sometimes intentional and desirable, such as in the case of a filter. But there are also many cases where frequency-specific behavior is unavoidable or undesired. And for this reason, most RF components have a specified frequency range over which they can or should be operated. But in addition to this frequency-specific behavior, RF components may also change their behavior based on the amount of power passing through them, and this power-specific behavior will be the focus of this presentation. Radio frequency components must be tested during design, verification, and production by generating a radio frequency signal at the component input. For components which do not terminate the signal, the output of the component is normally also measured. For example, a filter can be tested by applying either a wideband signal or signals at different frequencies to the filter input, and then measuring the output of the filter to ensure that the signals are being properly attenuated. This kind of stimulus response testing is performed either using a signal generator and a spectrum analyzer, or by using a special instrument called a vector network analyzer, or VNA, which incorporates both generation and analysis functions. Note, however, that there are RF component tests in which the output signal is not measured, and the main goal in this case is to verify that the component under test, or device under test, operates properly when RF is applied. For both types of testing, an RF stimulus signal must be created or generated. This RF stimulus signal must have an appropriate power or amplitude, and this depends on the DUT itself as well as the application or testing environment. There are three main cases when a high-power RF signal is required. The first is when power is split or divided among multiple low-power DUTs, in order to allow multiple DUTs to be tested simultaneously using a single high-power signal source. Another case is when the DUT normally operates with high input power. This is most often seen in aerospace, defense, and similar applications, such as in radar systems. The third case is when high power is used to stress the DUT for the purpose of testing reliability, useful life, etc., and this is a topic we'll cover in much more detail in just a few moments. There's no formal definition as to what high power is, but for RF testing, this usually implies a signal with powers above plus 30 dBm, or 1 watt. The definition of high power also depends in part on frequency ranges. As frequency increases, the definition of high power often decreases. In the case where the necessary stimulus signal power exceeds what the generating instrument can produce, an amplifier is used to provide the additional power. An amplifier is a device or component that amplifies a signal. That is, it produces an output signal which is a copy of the input signal, but with higher power or higher amplitude. Amplifiers are widely used in RF applications, and they can have both many different form factors, as well as very different performance with regards to things like gain, linearity, noise, etc. In the case of amplifiers used for high-power RF component testing, there are 4 general requirements. First, the amplifier should be a standalone device, which is externally connected to other instruments, such as signal generators or VNAs. The amplifier should be broadband, or be able to operate over a wide frequency range. And it should be able to produce a relatively high output power. It also should have a high Viswar tolerance. That is, it should be able to withstand high levels of reflected power. We'll talk about all of these in more detail later in this presentation. Let's look at how amplifiers are used in a typical component characterization test setup. As mentioned earlier, the stimulus signal is most often created using a signal generator, and the signal is then used as the input to an amplifier. The amplified signal is then injected into the device under test, or DUT, and a signal or spectrum analyzer is used to view the output of the DUT when appropriate. Alternatively, a vector network analyzer, or VNA, can also be used instead of the signal generator and spectrum analyzer, since VNAs have the ability to both generate signals and measure signals, although they often can only do this for very basic, single-tone, unmodulated signals. RF component testing can be divided into two general categories. The first is reliability or stress testing, in which the primary consideration is functionality. Is the component able to function under challenging operating conditions or over longer periods of time and large numbers of operating cycles? The second is performance testing, which is mostly concerned with how well the component performs. This may involve measurements of basic quantities, such as output power, or it may involve more complex signals and scenarios that require the use of a vector signal generator and spectrum analyzer. As the name implies, reliability or stress testing is used to determine how reliable the component is, usually over some period of time. Testing can be conducted under normal or expected operating conditions, and testing can also be conducted under stressful conditions, or conditions which might lead to degradation or even failure of the component. In both cases, but especially in the case of stress testing, significant amplification may be required to create an input signal with sufficient power to stress the DUT. Reliability or stress testing is used to determine both the mean time to failure, or MTTF, as well as the most common failure modes, that is, the cause or causes for failure in the component under test. Traditionally, reliability testing has been performed using simple continuous wave, or CW-type signals. But in recent years, the use of wider bandwidth, or modulated signals, has become more common when testing for reliability under realistic or real-world conditions. The reliability or useful life of most components follows something called a bathtub curve. This curve has three distinct regions. The first is often called infant mortality and corresponds to components which fail shortly after manufacture or initial use. In most cases, the cause for these early failures is some type of manufacturing or assembly defect. Once this infant mortality phase is passed, the component enters the useful life period, in which the failure rate is typically quite low and also remains more or less constant for a significant period of time. Failures during this useful life period are usually random with no clear cause or pattern. At the end of this useful life period, components enter the wear-out period, in which the failure rate increases again. As the name implies, failures in this region are primarily due to age or use-related wear, or are due to environmental conditions such as heat or vibration. Determining the limits of each of these three regions of the bathtub curve requires different types of testing. The three regions of the bathtub curve correspond to three different phases of high-power RF component testing. Infant mortality is investigated by means of burn-in testing. Useful life is determined using HTOL, or high-temperature operating life testing. And the wear-out period can be analyzed using HALT, or highly accelerated life testing. Let's look at each of these different types of testing in more detail. Burn-in testing is very common in manufacturing and is used for both quality control as well as to predict the infant mortality rate. This type of testing consists of both thermal stresses and electrical stresses. In many cases, burn-in is first performed at normal voltages, currents, and environmental conditions, but may then be performed again against higher than normal or higher than expected values. The thermal and electrical stresses can be constant or static, or they may be dynamic, with values being cycled over a range. As with most types of component testing, it may not be efficient or cost-effective to perform burn-in testing on every manufactured component or every component in a device, so sampling and statistical methods are often used. One important area of applications for amplifiers in burn-in testing is distributing the amplifier output power to multiple lower input power DUTs, since a single high-power amplifier can be used to test multiple components, and this allows for significant time, space, and cost savings. The operating life of an RF component is often strongly a function of temperature. Higher levels of heat tend to shorten useful life. HTOL, or high-temperature operating life testing, is used to help determine the expected operating life of a DUT when operated at high temperatures. It's important to note that this high temperature can come from two different sources. One is external or environmental heat. This type of heating is simulated by placing the DUT in a temperature chamber for testing. The other source of heat is internal or self-heating, created within the DUT itself during operation. All RF components dissipate some of their power as heat, and the amount of internally generated heat usually increases with input power or output power, with duty cycle, etc. In the second case, high-power amplifiers are often used to provide the input power needed to create significant self-heating. The purpose of highly accelerated lifetime testing, also sometimes just called ALT, is to determine both the average lifespan or useful device of an RF component, as well as that component's end-of-life failure mode or modes, that is, the mechanism responsible for the failure of the component. There are two methods that can be used, together or separately, to age the RF component. One of these is time compression. In time compression, the DUT is operated much more frequently than it would be under normal operation. For example, cycling the power on and off 1,000 times per minute, instead of the expected 10 times per minute. Another method of prematurely aging the DUT is by increasing the stress levels under which the DUT is operated. Environmental stresses include extremes of temperature, vibration, and humidity, either independently or in combination. Operational stresses most often involve subjecting the DUT to higher than normal power, for example, an input power of plus 30 dBm instead of the expected plus 10 dBm. Note that in order to provide valid results, the failure mode or modes at these higher stress levels must be the same as, or at least very similar to, those that would occur under more natural, lower stress levels. Now that we've covered reliability or stress testing, let's move on to discussing performance testing of high-power RF components. As the name implies, performance testing is used to verify that a component can meet the specified or required level of performance. There are multiple reasons why a component might not be able to perform as expected, and performance testing can be used to reveal these causes. One reason is design issues. The component is simply unable to meet performance requirements due to poor design, and therefore this most often necessitates a redesign of the component. Components may also experience a complete breakdown under certain operating conditions. That is, the component stops working entirely. But in some cases, the issue is performance degradation, in which the component does continue to function, but at a reduced level of performance. This may be a gradual change over time, such as an amplifier whose maximum output power slowly degrades over weeks, months, or years. Or it may be a degradation that only occurs under certain conditions, such as at certain input power levels, in different environmental conditions, etc. One thing to note about performance degradation is that it may be reversible, such as an amplifier that begins working normally when it has had time to cool off. Or the degradation may be irreversible or permanent. When a component breaks down completely, this is, of course, easy to determine, since the component typically is destroyed or stops functioning altogether. Similarly, simple degradation is also relatively easy to determine. An example of this would be a transmitter whose output power is n dB below the lower design limit. However, in many modern systems, signals have become much more wideband and/or modulated, and thus degradation only becomes detectable or measurable when more complex measurements are made. Both cases, simple and complex degradation, place requirements on the amplifiers used to detect and quantify this degradation. Although there are many performance measurements or metrics for RF components, in this presentation we'll look at the 6 most common ones. These are harmonic distortion, third-order intercept point, crest factor or peak-to-average power ratio, noise power ratio, adjacent channel leakage ratio, and error vector magnitude. We'll start with harmonics. High input power levels can drive an active component into compression and cause it to generate harmonics, which are copies of a signal that appear at integer multiples of the fundamental frequency. Although they can be useful in some cases, harmonics are generally undesirable because they create interference, distort signals, and can contribute to the creation of so-called intermodulation products, something we'll discuss in detail shortly. In addition, the power in these harmonics is power that's taken away from the fundamental output signal. The most common way of suppressing harmonics is by means of low-pass filtering. The levels of harmonics and the distortion created by these harmonics can be measured in 2 different ways. The first is by measuring the power in each individual harmonic, and this is typically done relative to the power of the fundamental. That is, the result is in units of dBc, or decibels down from the carrier. Another way of quantifying harmonics is total harmonic distortion, which is a measure of the sum of power in the first n harmonics. This quantity is also often expressed relative to the power of the fundamental, in units of either percent or dB. Harmonic distortion measurements are almost always made using a spectrum analyzer. Although it's possible to measure harmonics manually by placing markers on individual harmonics and then manually calculating total harmonic distortion, many spectrum analyzers have a harmonic measurement application that can do this automatically, and this is considerably faster and more precise than manual measurement and calculation. Unlike harmonic distortion, which only requires a single input signal, intermodulation products are generated by the mixing of 2 or more signals or tones in nonlinear components. The output will contain not only the original 2 signals, but also signals at the sum and difference of the 2 input signals. In addition to mixing with each other, the input signals may also mix with harmonics. For example, there may be intermodulation products created by the first harmonic of one tone and the second harmonic of the other tone. Note that the order of harmonics or intermodulation products is simply the sum of their unsigned coefficients. That is, both 2f2 minus f1 and 2f2 plus f1 are third-order products. Intermodulation products can be formed from many different combinations of the fundamentals and various harmonics. 2 third-order harmonics are, however, particularly troublesome or difficult to deal with, namely 2f1 minus f2 and 2f2 minus f1. Although there are other third-order harmonics and products, these 2 are very close in frequency to the fundamentals, or wanted signals, and thus it's difficult to use filtering to remove these products. In addition to being difficult to remove by filtering, the amplitude of these products grows more quickly than the amplitude of the fundamental. In fact, when a signal is amplified, the third-order products increase in amplitude at a rate 3 times that of the fundamentals. In other words, the fundamental has a slope of 1, but the third-order products have a slope of 3. Looking at this graphically, it would appear that at some input power level, the amplitude of the fundamentals and third-order products would eventually meet. However, the amplitude of the fundamental and the amplitude of the third-order products do not meet because of something called compression. The device simply can't output power beyond a certain level. However, we can still calculate the point at which the fundamental and the third-order product amplitudes would meet, and this point is called the third-order intercept point, often abbreviated either TOI or IP3. Third-order intercept is normally measured by using a signal generator to create two input tones to the component under test, and then measuring the amplitude of third-order intermodulation products present at the DUT output. Third-order intercept is an important measure of the linearity of a component, and thus a high IP3 is almost always desirable. Next, we'll discuss peak-to-average power ratio, which is simply the ratio of the peak signal power to the average signal power. This is often also referred to as peak-to-average ratio or crest factor. Peak-to-average power ratio can be thought of as a measure of the burstiness of a signal, because higher values indicate a signal whose peak levels are significantly higher than their average level. This actually is quite common in newer digital modulation schemes. For example, GSM, a 2G cellular technology, uses a modulation type that has a peak-to-average ratio of 0. But peak-to-average ratio has been increasing with each successive generation of cellular and Wi-Fi technology. This is important because signals with a high peak-to-average ratio can be very challenging. They require a high dynamic range in ADCs and DACs, and they often require highly linear amplifiers with high peak power capability. In most cases, peak-to-average ratio is measured using a spectrum analyzer and is reported as a numerical value in dB. But it can be helpful to look at peak-to-average ratio as a curve, where it's usually plotted in the form of the complementary cumulative distribution function, or CCDF. A CCDF curve shows how often a given peak power is reached. The further the curve moves to the right, the greater the peak-to-average ratio. In some cases, component behavior can be analyzed or quantified by measuring CCDF at both a component input and output. For example, this is the CCDF curve of our input signal. After passing through the component under test, we again plot CCDF. Since the CCDF curve at the output has moved to the left, this indicates a lower peak-to-average ratio at the output, which in turn strongly suggests that our component under test, here an amplifier, has gone into compression and can no longer faithfully reproduce the peaks of the input signal. It's important that an amplifier placed before the DUT input not be in compression, since this would make it difficult or impossible to separate the distortion introduced by the DUT from the distortion created by an overdriven amplifier at the DUT input. The next topic is noise-power ratio. Traditionally, most RF transmission systems used a single carrier to transmit information. More recently, wider bandwidth systems now often use some type of multi-carrier transmission scheme. Examples include satellite systems, terrestrial microwave, etc. One potential issue in multi-carrier systems is that these carriers may mix, creating undesired intermodulation products and intermodulation distortion. In order to measure this intermodulation distortion, a measurement known as noise-power ratio is used. Noise-power ratio, or NPR, is measured using a signal generator to create the input signal and a spectrum analyzer to analyze the output signal. Testing noise-power ratio requires a wideband signal that contains a deep notch, or unused channel. This notch signal is then input to the component under test. Intermodulation distortion will cause the notch to partially fill with noise. This is sometimes referred to as spectral regrowth. The new notch depth is measured using a spectrum analyzer, and noise-power ratio is then the ratio, in dB, of the carrier power to the notch power. A higher noise-power ratio, or less noise in the notch, means lower intermodulation distortion. Note that the size, location, and number of notches are chosen based on the given DUT or application, and NPR tests are often repeated with different notch counts, sizes, and locations. As with the previous example, it's important that high-power NPR testing uses an amplifier that sufficiently amplifies the notched input signal, but does not introduce its own intermodulation distortion. Adjacent channel leakage ratio, or ACLR, is another form of intermodulation distortion. Most modern wireless data systems assign modulated carriers to a channel with a given bandwidth. The power of a channel is defined as all the power that falls within that channel, and is found by integrating over the channel bandwidth. This is an absolute power measurement with results in units of dBm. Ideally, all of the power of the transmit signal would stay within the channel, but intermodulation distortion can cause some of the transmit signal power to fall outside of the channel or leak into adjacent channels. Not only is this inefficient, but more importantly, it can also create interference to signals in adjacent channels. Because of this, ACLR is one of the most important measurements in wireless communications. ACLR is measured using a spectrum analyzer, and, as the name implies, ACLR is a ratio. It's computed by comparing the power in the transmit signal channel to the amount of power that leaks into one or more adjacent channels. This is found by summing up or integrating the power in each channel, and the difference between these powers is ACLR. Since ACLR is a ratio, ACLR results are normally expressed in dBc, or dB down from the carrier, and therefore will always be negative. Although we're only showing 3 channels here, note that ACLR can also be computed for power that leaks even past the adjacent channels into so-called alternate channels that lie even further away from the transmit channel. The last performance measurement we'll look at is error vector magnitude, or EVM. Many digital schemes are based on symbols, which are unique combinations of amplitude and/or phase values. Each symbol represents certain bit patterns. In the example on the right, we see a constellation of 16 symbols, represented as vector endpoints, and each of these endpoints corresponds to a unique pattern of 4 bits. By alternating the amplitude and phase of our carrier, we can alter which set of bits we're transmitting. In practice, however, the received or measured symbol points usually don't fall exactly on the ideal reference points, and this can happen for many reasons. If a received symbol point is too far from the reference point, that symbol or point may be incorrectly interpreted, and bit errors will occur. The greater the distance from the ideal or reference point, the greater the probability of bit errors. The most common way to quantify this distance between the measured or actual point and the ideal point is something called error vector magnitude, or EVM. The ideal or reference point has a defined magnitude and phase, but the received or measured points rarely fall exactly on the ideal point. Part of the difference may be due to magnitude error, that is, the received vector is too long or too short. And part of the difference may be due to phase error, where the angle of the received vector is incorrect. We can quantify these 2 sources of error by drawing a vector that connects the reference and measured points, and this vector is referred to as the error vector. Like all vectors, the error vector has both a magnitude and a direction. In digital signal modulation, we are mostly concerned with how far we are from the ideal point, not the direction to the ideal point. So the important measurement is the error vector magnitude, or EVM. EVM is usually reported in percent, and larger values of EVM indicate greater distance between the measured and ideal points. Greater distance means a higher probability that the receiver will mistake one symbol for another, and thus higher EVM values mean a greater probability of bit errors. One challenge in EVM testing is the need to produce a DUT input signal with low EVM in order to minimize the generator contribution to EVM measured at the DUT output. Often EVM is shown in the form of a bathtub curve with three distinct regions: an area where EVM is poor because of low signal-to-noise ratio, a region where optimal EVM can be obtained, and a region where EVM increases due to compression. The vector signal generators used to create the modulated signals needed for EVM testing may not have a sufficiently large optimal region for testing DUTs which require a large input power, such as cellular base stations. Amplifiers are therefore necessary when testing EVM for devices which require high input power. By placing an amplifier between the vector signal generator and the device under test, the EVM bathtub curve can be effectively shifted in order to provide optimal EVM performance over the required input power range of the device under test. Now that we've covered the most important measurements made during high-power RF device characterization, let's now discuss the requirements for amplifiers used in this testing. At a very high level, the amplifier must be able to produce the desired gain, or output, and it must be able to do so without excessively degrading or distorting the signals passing through it. The latter requirement is very important when it comes to performance-related degradation. We want to be sure that the measured degradation is coming from the component under test instead of from the amplifier. In more concrete terms, the key amplifier characteristics for RF component characterization fall into three main categories: Viswar tolerance, gain and compression point, and linearity and harmonics. Let's look at each one of these topics in more detail. Recall that in burn-in, HTOL, and halt testing, a common outcome is failure or even destruction of the component itself. A component that fails catastrophically may become either an open or a short, and in this case, the failed DUT would reflect all of the power that it receives back towards the amplifier. The level of reflected or reverse power relative to the level of forward power is usually quantified by means of voltage standing wave ratio, abbreviated VSWR or Viswar. High levels of reflected power can easily degrade or damage some amplifiers. But high Viswar can also be encountered even during normal testing, and in this case, an amplifier with a low Viswar tolerance would have to reduce its output power, or fold back, in order to prevent amplifier degradation or damage. Therefore, there are two reasons why high Viswar tolerance is desirable in amplifiers being used for high-power RF component characterization. First, it helps prevent amplifier damage if, or when, a component under test fails catastrophically. But a high Viswar tolerance also enables the amplifier to safely generate higher output powers, particularly in the case when Viswar is high during normal testing. High Viswar tolerance becomes even more important for automated or unattended operation, that is, in cases where a manual operator cannot recognize and respond to sudden or unexpected changes in reflected power levels. Another defining characteristic of an amplifier is its gain and compression point. Gain is the amount of amplification provided by the amplifier and is usually expressed in units of dB. Although the amount of gain needed will vary depending on the test scenario and the component under test, it's important that the amplifier have sufficient gain to stress the DUT under all test conditions, including cases where high Viswar is present. Although amplifiers normally have a linear gain, at some input power level, all amplifiers no longer have a linear output. That is, the output no longer increases by n dB when the input increases by n dB. This situation is referred to as compression. Compression is most often quantified in terms of P1 dB, or the 1 dB compression point. This is the input power at which the actual amplifier output is 1 dB less than the expected linear output. Generally speaking, a higher P1 dB is always desirable. It's important to ensure that P1 dB is higher than the peak rather than the average value of a signal. Note too that aside from the reduction in gain, operating in compression has additional drawbacks. Components in compression often create nonlinearities or distortion in their output. Ideally, the output of an amplifier would be a perfect copy of the input, only with greater amplitude. However, when an amplifier is operating in compression or in its nonlinear region, this can lead to the creation of spurious signals and/or distort the amplified signal. Poor linearity has several consequences. First, the power in spurious products is wasted power that's not being used to amplify the input signal. But more importantly, poor linearity can make it very difficult to determine if distortions are being created in the component under test, or if they're being created in the amplifier itself. Therefore, it's important to minimize the amplifier's contribution to nonlinearity and distortion by choosing an amplifier that can provide the necessary linearity required for characterization of a given component. Let's summarize what we've covered. Amplifiers play a crucial role in high-power RF component characterization, and they're frequently used in design, verification, and production. These high-power amplifiers are needed both when testing for reliability, as well as when testing components requiring a high drive level. In this presentation, we discussed two general categories of RF component testing. Reliability testing consists of three phases: burn-in, H-tall, and halt, which correspond to the three regions of the component lifespan bathtub curve. With regards to performance testing, we briefly discussed some of the most common tests, such as harmonics, IP3, peak-to-average ratio, EVM, etc. When selecting an amplifier for use in component characterization, the three most important parameters are good visual and fault tolerance, sufficient gain and appropriate compression point, and high linearity. This concludes our presentation, The Role of Amplifiers in High-Power RF Component Characterization. Thanks for watching.